So, training large language models is notoriously hard and expensive. From having to source trillions of tokens of data and having to spend hundreds of thousands to even millions of dollars in compute, it has become very cumbersome for independent researchers and even smaller labs to be able to train their own models. In this video series, I'm going to show you a new approach that will allow us to create a new large language model in just under $300. This is a continuation of our coding Llama 2 from scratch series. And the great thing is that we are starting with Llama 3, the newest and most recent model from Meta AI. So let's get started. If you're new here, for me, please like, subscribe, and turn on your notifications to be notified of future videos. So in this series, we are gonna start from 3 ideas and build upon them throughout the series. And these are the ideas that led me to believe that there is a new way and more efficient way of creating new models. So the first idea out of the 3 is called upcycling. And it comes from this paper called Sparse Upcycling Training Mixture of Expert Models from Dense Checkpoints. And the idea is very simple yet super powerful. You have a dense model and you use the weights of that dense model to initialize a new mixture of experts model. And you can see here you copy the weights of the layer norm, the attention, the MLP. So in particular, mixture of expert models use multiple multi-layer perceptron, right? So what you do is you take the existing pre-trained multi-layer perceptron layer and copy the weights across all of the experts, right? And the only layer in this new model that's not initialized is the router, given that we don't have anything similar in a dense model. But in this case, the router is really quick to learn, so you can train that from scratch. But the majority of the model has existing pre-trained weights, and that reduces computation significantly. And I can show you that here. So in the paper, they also have this graph here that shows you on the x-axis how much time it took to achieve a particular accuracy. And you can see that the dense model converges much slower compared to the mixture of expert model initialized from a pre-trained dense checkpoint. And you can see here the token accuracy. At the bottom here, we have a base model that was initialized. This one is a dense model. And you can see that the performance doesn't really move much for this model if you increase the pre-training time. But for the mixture of expert model that was initialized from pre-trained checkpoint, right, of a dense model, it achieves a significantly better performance compared to the dense one. And the same is for a large model and a super large model as well. So you can read more about this idea of upcycling in this paper here. But the most interesting thing for me when I read this paper was thinking about the opposite. So here we are taking a dense model and turning it into a bigger model, right? A mixture of experts model. It doesn't have to be sparse. It could be a dense mixture of expert model, which would still make it a significantly larger model compared to the base one. And I thought, what if we could go the opposite direction, from a bigger model into a much smaller model? And I've been thinking about this for some time, ever since last month. And more recently, actually last week, I came across a very interesting paper. And this paper is called Pre-training Small Base Language Models with Fewer Tokens. And it has exactly the idea that I was thinking about. They call it inherit-tune, so inherit the weights and fine-tune. But I prefer downcycling. I think it's a bit more befitting of this technique. And the idea of downcycling, or inherit-tune if you prefer, is to take a reference model, copy all of the weights, but with one caveat. And you copy the weights of the layers of this model up to n. So n in this case is smaller than m, where, for example, our reference model has 32 layers, right? And our new target model has 18 or 16 layers. So you copy, out of the 32, you copy only 16 or 18 layers. And then you leave out the rest, right? And when I say copy the layers, keep in mind that we are only skipping the layers in between, but we are keeping the embedding and prediction head and normalization layer, which you will see later when we go into the coding example. So you copy the n layers, right, out of the m, and you initialize a new model with n layers. And we can go into the details of why this works. So the abstract is a very, very interesting place to start. And actually, I think this sums up the paper really well. Here they say, we call our simple recipe inheritune and first demonstrated for building a small base language model with 1.5 billion parameters using a billion tokens. Think about that. You are creating a new model that has 1.5 billion parameters, and you're only using 1 billion tokens to train that model. And here's the interesting part, is that that model was downcycled from a 3 billion parameter model, and they did this with a single A6000 GPU and in less than half a day, meaning in less than 12 hours, they had this model up and running. And across 9 different diverse evaluation datasets, as well as the MMLU benchmark, the resulting model compares favorably to the publicly available base models with 1 billion and 2 billion parameters in size, some of which have been trained with 50 to 1,000 times more tokens. So this 1.5 billion parameter model that was trained on only 1 billion tokens has similar performance to models that were trained with 50 to 1,000 times more data. And then they go on to say, here we show that a smaller language model or smaller language models trained utilizing some of the layers of GPT-2 medium, 355 million parameters, and GPT-2 large with 770 million parameters, can effectively match the validation loss of the bigger counterparts that were trained from scratch for the same number of training steps on open web text dataset with 9 billion tokens. So you're saying that if you train a model from scratch and you have another model that was initialized from a pre-trained base model or even instruct, you can match the performance of the model that was trained from scratch in the same number of steps. And you can do that much faster. So here we have the algorithm as I illustrated above. So that graph comes from this algorithm here. So we can go through it just so that you can kind of see this. It says the reference model and a subset D-train hat from D-trained used to train the reference model, the number of layers we want, n layers we want in our final model, and the number of epochs and training hyperparameters. So number 1, let K be the number of transformer blocks, right? K be the number of transformer blocks in MREF on our reference model, with the corresponding parameters being theta 0 and so on. These are the weights. We initialize a target model with the first n layers of the reference model, as well as the token embedding and prediction head layers of the reference model, right? So you're only ditching a small subset of layers of the reference model, but you're keeping the architecture intact. So number 3 says, train the target language model from this initialization for epochs using the given hyperparameters. So now let's go into the evaluation section of this paper. You can see here that they have their 1.5 billion parameter model that was trained using downcycling, And they're comparing that model with shared Llama 1.3 billion. They're comparing it with the MPT 1.3 billion parameter model. And they're also comparing it with OPT 1.3 and Pythia 1.4. In this graph, we have the tokens in billions in our x-axis, and here we have the average score for a downstream task. And you can see that the model that was trained using this technique, the Inheritune, achieves comparable performance to models that are trained with 50 times more data and up to 300 times more data. That is super impressive. With only 1 billion tokens, you can achieve similar performance to a model that was trained with 300 times more data. That is super impressive. And the same goes for the MMLU score, where they use 5-shot examples. And here on our x-axis, we have tokens in billions. And the performance is quite impressive again. The model that was trained with 1 billion tokens using this downcycling technique outperforms all the models that were trained with 300 times more data and achieves comparable performance with models that have 50 to 200 times more data, and achieves comparable performance to models that were trained with 50 to 200 times more data. That is super impressive. Now, here we are seeing what they talked about in the latter part of the abstract. You have a full model in the green line here for both graphs. And in this case here is GPT-2 large. It has 36 layers. And here we initialize the model using the downcycling technique. And you can see from this graph that the downcycled model achieves comparable performance in the same number of steps, but actually it converges much faster compared to the pre-trained model. And the same goes for GPT-2 medium. And finally, on this paper, there's this part that was pretty interesting to me, where they are comparing the number of tokens and number of epochs to achieve a particular performance. So the first one, as they presented, is the 1.5 billion parameter model trained on 1 billion tokens for 10 epochs. So you're repeating the billion tokens for 10 times. And you achieve 24.95 on the MMLU score. You would think that more data would mean more performance, but that didn't prove to be true here, because they trained another model with 50 billion tokens, where each epoch there were new tokens, new 10 billion tokens, and you can see here that it achieved an inferior performance to training for 1 billion tokens for 10 epochs. And here they increased the number of epochs from 10 to 20, and they achieved a new high of 25.46. And again, you would think that increasing the data set would make a difference. In this case, they kept the 50 billion, but every epoch, the model saw 20 billion new tokens, and that achieved a comparable performance to the first benchmark of using only 1 billion tokens and 10 epochs. This goes to show that using a smaller data set and increasing the number of epochs is your go-to when it comes to this particular technique. Perhaps, yes, we're gonna explore and validate some of these claims throughout this series. So let's continue. Our final idea before we dive into the code is called Infini-attention. The idea of Infini-attention is that you can increase the context length of the model you have infinitely. You are only limited by the compute and storage you have. In the paper, they describe that they can increase In the paper, they described that they can increase the context window infinitely. And what caught my attention are two things. First, there's no major changes to the architecture of a transformer. Second, they managed to take a billion parameter model and increase the context length of that model to 1,000,000 tokens, which is quite impressive. We can have really small models that have really great context windows. It would unlock a lot of interesting use cases. So how does it work? Alongside your attention mechanism, you have what they call compressive memory. It's a linear layer at the high level that takes in your key values. Instead of you caching these, you pass it through this layer and it keeps the representation of this layer, and you can retrieve context from any of the previous keys and values using only your queries. So you pass on your queries, and then after you retrieve that extra context, you merge it back with the attention scores, and then you can pass it on to the model. It's another very interesting yet powerful idea, and it's from this paper called Leave No Context Behind. Another very interesting thing is that I managed to contact one of the authors of this paper that has created a GitHub repo with all of the code for this paper that we will be using to integrate it to our own models. And if we come across any bugs, I'll be contacting him for help. Shout out to him and shout out to all of the authors of the papers here. So now let's go into the code. The code is in the Coding LLMs from Scratch repo. I'll be sharing that in the description below. And here you have Llama 2. You will go into Llama 3, Part 1, Downcycling. That's the notebook that we'll be using here. And first we are installing transformers, torch, accelerate, Hugging Face Hub, Hugging Face CLI, and Hugging Face Transfer. So Hugging Face Transfer is going to help us download the models much faster. Hugging Face CLI and the Hub are going to help us communicate with the Hugging Face platform. Then we have Accelerate, Torch, and Transformers that are going to help us with the model, like loading the model and be able to run inference. So here we are just going to initialize a function that I created to count the parameters of the model in billions. So here I'm going to run this. And here I will load an instruct model. So here's the Meta Llama 3 8B instruct model. So this will be our reference model. And we might want to just to double check, we will put here model. There we go. The model is loaded. So now let's run the count parameters. We can see that it has 8 billion parameters as advertised. And let's look into the model. So this is the architecture of the model. We have our model wrapper here on top. And then within that model, we have the embedding layer, and we have all the different layers with the attention mechanism, our MLP, normalization, right? After the layers, we have another normalization layer and our prediction head. So now that we have seen that, I'm going to create here a function to extract the model weights. So we are going to extract up to n layers of the reference model. So it just takes those two arguments. And what's happening here is that we are iterating over the model layers. We are copying the weights and biases of any layer, right? And then here we are checking if the layers have gotten to where we want them to. And here we're just checking if the current layer is bigger than the number of layers minus 1. Since counting starts from 0, we have to subtract here the minus 1. And if that is true, we're just gonna get out of this loop. And after the loop, you notice that we have the normalization layer and then the prediction head. And we want to copy those as well. So we are keeping the architecture the same, just reducing the number of layers. And we can run that. Once we run it, we are going to get 24 layers out of the 32 layers that Llama 3 8B instruct has. So this will just take a few. Okay, so now we have the pre-trained weights here in this variable. those are the 24 layers that we wanted. Here we are just going to initialize an empty model, a model without any pre-trained weights. And you can do that by using the from config instead of from pre-trained. And here we are just changing the configuration that we, instead of 32 layers as the default model has, we want 24. And once we do that, it's going to take a minute to load the model to memory. There we go. So it took about a minute to load that model. Now we can count the parameters of this model, and we can see here that we have 6 billion parameters. So instead of the 32, we took 24, and now we have 6 billion parameters. So now we're gonna load the weights of the 24 layers from the pre-trained model into our target model. And you can see here all keys matched successfully, meaning that all of the layers were loaded successfully. And here we have a question. It says, giving the question, read the article and select the best answer. The article, can you swim? Do you like swimming? And so on and so forth, right? And here's the part that's interesting. There is a question that the model needs to answer. And the question is, which is the best title for this passage? How to learn English, easier said than done. Listen first, speak second. How to learn how to swim. The correct answer is how to learn English. And let's see if the model can answer it correctly. So here we load and we are going to stream the answer. So let's see. Accordingly, answer is the option A, how to learn English, which is correct. Now let's see if it can reason. Because although there are mentionings of other topics such as how to learn to swim initially followed by how to learn English, but main focus of this essay is how to learn English rather than other topics. Therefore, the best title would be option A, how to learn English, rather than other options which are secondary topic rather than the main topic, which is pretty good. Of course, we can fine-tune the model to do even better, and the idea is to start from this base model and create something new. We are creating a new Llama 3 6 billion parameter from the 8 billion. And the interesting part is that I'm also working on other models such as the 45 and 35 billion parameters that are derived from the much larger 70 billion parameter model. And finally, we are going to upload that model and the tokenizer into the Hugging Face Hub. So in this case, if we go here, let me open my Hugging Face page, Prince Kanuma, and you can see here that I already created a couple models. So the Llama 3 6B instruct and also the base model using this downcycling technique. As well as I'm working on the 46B, this one just uploaded, and I'm working also on the 35 billion parameter version. So from here, in the next video, we will have the fine-tuned version. I'll walk you through the fine-tuning process that I will go through, as well as in that next video, we will start exploring Infini-attention. So how can we implement Infini-attention into this new type of models? And from there, we'll see what else we can do. But until then, looking forward to it and catch you on the next one. Bye-bye, bye-bye.